Okay, so here we got the notes for section 5, which deals with linearization, sensitivity, and differentiation. So when we talk about linearization, we're talking about a linear approximation. So if f is differentiable at x equals a, then the equation, the tangent line, L of x is equal to f of a plus f prime of a times x minus a, defines the linearization of f at a. The approximation f of x approximate L of x is the standard linear approximation of f at a. The point x equals a is the center. Now, one thing to be careful of, remember, f of a is a single value. F prime of a is a single value. So it's not f prime times a times x minus a. This a and that a are part of the function notation that goes in front of them. Okay, so example 1 says find the linearization of f of x equals the square root of 1 plus x at x equals 0, and use it to approximate 1 plus, or square root of 102 without a calculator. So f prime of x, because we need our derivative, is going to be 1/2 quantity 1 plus x to the negative half. For this problem, our a value is 0. So to build our equation, we need f of a, which we get by plugging 0 into the original equation. So L of x, so f of a is going to be 1. If we plug 0 in here, 1 plus 0 is 1, square root of 1 is 1. Plus, then I plug 0 into my derivative. So 1 plus 0 is 1, 1 to the negative half is 1, 1 times a half, so this part is all just 1/2. And then I have x minus 0, or just x. So use this to approximate the square root of 102 without a calculator. So the one thing we do have to be careful of is that our x value isn't the 1.02, it's the 0.02, because f of x is already 1 plus x, so the x value is what I'm adding here. So I'm finding L of 0.02. And if I work this out, this gives me 1.01. Now, if I just do the flat number in the calculator, I get 1.00995. So they are pretty close to each other. So what this is kind of illustrating is that any curve can be approximated with a straight line, and L of x is that approximation. Now, the farther you get away from your center point, the less it works, but you can still do it the same way. All right, find the linearization of f, or cosine x at pi over 2, and use it to approximate the cosine of 1.75 without a calculator. Use a calculator to determine the accuracy. So we need f prime. So the derivative of cosine is the negative sign. So the linear approximation is f of a, so plug pi over 2 into my equation, which is 0, plus f prime of a, so plug pi over 2 into this, so that's going to be -1, and then it's going to be x minus pi over 2. So the linear approximation in this case is just -x plus pi over 2. So if we want to do approximate 1.75 without a calculator, so we would plug 1.75 in for x, so -1.75 plus pi over 2, which comes out to be about -0.18. And if we just flat out calculate the cosine of 1.75, we get -0.18 as well. So they match very, very well. No, I actually did this one wrong. That actually should have been a 102. I was cheating to make it come out right, which makes this actually 1.51. That's because we're finding a value far from our center. We're doing the square root of 1, and we centered it at 0, so it doesn't quite work as well. Okay, so example 3 here says, example 1 introduces a special case for linear generalization that applies to powers of 1 over x for small values of x. So 1 plus x to the k is approximately 1 plus k to the x. If k is a positive integer, this follows from the binomial theorem, but the formula actually holds for all real values of x, or k. I use this formula to find polynomials that approximate. So this is 1 minus x to the 1/3. This is 1 minus x to the negative 1. This is 1 plus 5x to the 4th to the half. And this is, let's see here, we'll rewrite all these first. 1 minus x squared to the negative half. So then we just need to go back and figure out what these all come out to be. Okay, so getting the work done here. So I do need to kind of rewrite this. So this is 1 plus negative x. Then you have the form 1 plus. So this linearization would be 1 plus the k value is 1/3, and my x value is actually negative x. So this would be 1 minus 1/3 x, or you could write it as 1 minus x over 3. So this one, similar thing's going to happen. This is 1 plus negative x to the negative 1. So the linearization would be 1 plus the k value is negative 1, negative x, so 1 plus x. So down here, let's see here. So this whole guy is going to act like my x value. So the linearization is going to be 1 plus k 5x to the 4th. So that's going to be 1 plus 5 halves x to the 4th. I actually shouldn't really be using L here because that's not a linearization. It's not an L value anymore. Here, so this is going to be 1 plus negative x squared to the negative half. So 1 plus negative half times negative x squared. So that would be 1 plus half x squared, or 1 plus x squared over 2. Okay, use linearizations to approximate the square root of 123 and the cube root of 123. So we're going to, we need to find a place to center it. So you normally want to center it at the closest perfect, or in this case square. So we're going to center this one for part A at 121, because that's the closest perfect square. So the linearization is f of a plus f prime of a times x minus a. So f of a is 11, so this becomes 11. Let's see here, plus, so the derivative of, so we're doing the square root function. So we need to take the square root. So the derivative of that would be 1/2 x to the negative half. So if I plug my 120 into that, I get 1 over 22. That's going to be x minus 121. So that's my L of x. So then to approximate 123, I would plug my 123 in for x. So the linearization for 123 is 11 plus 1 over 22 times 123 minus 121. So 11 plus 1 over 22 times 2. So 11 plus 1/11 would be my answer, which comes out to be, no, that'd be my approximation actually if I convert that. So that's 122 out of 11. Count the decimal, that's about 11 point, whoops, off the bottom of the screen. 09. So over here, for 123, we need the closest perfect cube. So for B, we're going to center at 125. And this equation is the cube root of x. So for L of x, 125, its cube root is 5 plus, So the derivative of the cube root is 1/3 x to the negative 2/3. So if I plug 125 into that, 125 to the negative 2/3 times 1/3, that is 1/75. Then x minus 125. So if I want to do 123, 5 plus 1/75, 123 minus 125. So that's 1/75 times -2. So 5 minus 2/75. So 5 is 375. So that's 373/75. Or as a decimal, that's 4.973 repeating. So this is actually how we did square roots and cube roots a long time ago. Okay, so differentials say let y of x be a differentiable function. The differential d of x is an independent variable. The differential dy is given by this. So this is kind of rearranging this notation. The dy dx, the same thing as f prime. So it says find the differential dy and evaluate dy for the given values of x and dx. So it's f prime, so I need to take the derivative. So dy will equal 5x to the 4th plus 37, that's the f prime part, and then times dx. Now it gives me a value for x and a value for dx, so I can plug those in. So 5 times 1 to the 4th plus 37 times 0.01. So that's 5 plus 37, so that's 42. 42 times 0.01 is 0.42. So dy is 0.42. And let's see, look at the next one. Okay, so for this one, so dy equals, so the derivative of that is 3 cosine 3x times, just dx. So plug in our values. So 3 cosine 3 pi, negative 0.02. So 3 cosine 3, excuse me, 3 cosine 3 pi is negative 3 times negative 0.02, so that's positive 0.06. And the last one here. Okay. So we need to do some implicit differentiation here. So what's going to happen is that every time, there's too many equal signs here. What's the problem? Oh, that shouldn't be there. X plus y equals xy. So derivative on the left, so that's going to be 1 plus, and this is going to become a dy, or y prime, essentially. And this is going to equal, so that's a product rule. So what's going to happen here is we're going to have, oh, no, sorry, we're not doing, we're leaving these in terms of dx, sorry. So this is going to be dx times y plus x times dy. Because we know a dx value, so we have to leave our x in terms of dx's. So everybody with the dy comes left, so this is dy minus x dy equals y dx plus dx. So over here I can factor out the y, or dy, so dy times 1 minus x. Over here I can actually factor as well, factor dx out. So dy is equal to y plus 1 times dx, just reverse the order, over 1 minus x. Now the problem is here I need the y value. But since I know what x is, I can plug it in here and actually figure out what y is. So 2 plus y is equal to 2y. So 2 is equal to y. So dy is equal to 2 plus 1, dx is 0.05, all over 1 minus 2. So this is 3 times 0.05 over negative 1. So dy is negative 0.15. Yeah. Oops, nope, that's negative. Which means this should be minus, which means this should be 1, which means this should be negative 0.05. All right, sensitivity. Sensitivity is an interpretation of the derivative, describing how small changes to the input produce change in the output variable, which is literally what we just did. So dy is so a small change in the input, dx, produces some small change in the output, dy. For small values of delta x, we can approximate it with this formula, which looks super similar to the one we just did. Dy dx is the derivative, delta x is the change in the x value. Okay, so example 6, the radius r of a circle increases from 10 meters to 10.1 meters. Use the linearization to estimate the increase in the circle's area. Compare this estimate with the true change in delta A and find the approximation error. So here we go. So let's see here. The area of a circle is pi r squared. So the derivative is 2 pi r. So it's the derivative times. So to find out, so delta A is given by 2 pi r times delta r. So our radius is 10, so 2 times pi times 10. Delta r is 0.1, the difference between the two radii. So this is 20 pi times 0.1, so that's 2 pi, so about 6.28. So this is compare this estimate with the true change. So the true change is we have to calculate the two areas. So area when the radius is 10 would be pi times 10 squared. The area when it's 10.1 would be pi times 10.1 squared. So this is going to be, so 10.1 squared is 102.01 pi minus 100 pi, be 2.01 pi. So that's the true change, 2.01 pi. The approximation error, we'd find the difference and then divide by, no, it's just the difference, sorry. So the error, I was going to find percent error, is 0.01 pi. So that's the actual change in the radius, that's the approximated. Okay, absolute, relative, and percent change. So absolute change, you have this formula, true. So that's how you would calculate if you wanted the actual value, which is what we did up here. Estimated, which is what we did on the right over here. Relative change, you divide delta f by f of a, or here, f prime of a divided by f of a times delta x. And then percent change just takes relative change times 100. So it says here, inflating a bicycle tire changes the radius from 12 to 13 inches. Use the linearization to estimate the absolute change, the relative change, and the percent change. Perimeter of the tire. So we're using the estimated over here. So for absolute, delta f, so let's see here, perimeter of the tire. So the circumference of a circle is 2 pi r. So c prime is, the derivative is 2 pi. Okay, so let's see here. So it's f prime of a, so f derivative is 2 pi, delta x is 1, so the absolute change is 2 pi. Sorry, that should be, we'll use c for circumference. The relative change, let's see here, is the derivative, so the derivative is 2 pi over the actual equation, 2 pi r times delta r. So that's going to be 1 over r times delta r. So 1/12 times 1, or just 1/12. And then the last one, I'll make this a decimal because we're going to need it for the next one. Whoops. So this is 0.083 repeating. So then the percent, you would just take this number times 100. So that would be 8.3% approximately. Okay, so example 8 here says, suppose the Earth were a perfect sphere, and we determine its radius to be 595 plus or minus 0.1 miles. What effect the tolerance have on our estimate of the Earth's surface area? So the surface area of a sphere is given by 4 pi r squared. So let's see here. So we would need, so delta S would be 8 pi r, the derivative, times delta x. Let's see here. And then we plug our numbers in. So 8 pi, the radius is 3, delta x is 0.1. So come out to be 8 times pi times 3959 times 0.1. So 9950.1 square miles would be how far off we could be. So quite a bit by just having even a tenth at that point. Okay, example 9 here. About how accurately should we measure the radius to calculate surface area to within 1% of its true value. So let's see here. So we want be small to make, let's see. So we want 8 pi r delta r, so that's our error, to be less than or equal to 1%. So the actual value would be 4 pi r squared. So that'd be 1% of the actual value. So now we just need to solve for delta r. So I need to multiply that guy across. So delta r is less than or equal to, let's see here, 1 over 8 pi r. So divide that guy across times 4 pi r squared over 100. So this comes out to be pi's cancel. That cancels, leaves me an r up top. That cancels, leaves me 2. So 1/200th of the actual radius is how accurate we would have to be. Or 0.5%. Sorry, I had to get a new pen. All right, example 10. In the late 1830s, the French physiologist Jean Poisson, I don't even want to try to pronounce that. So the formula used today predict how much the radius of a partially clogged artery has to be expanded to store normal flow. This formula V equals KR to the 4th. Says the volume of fluid flowing through a small pipe in a unit of time at fixed pressure is a constant, which is K, times the 4th power of the tube's radius. How will a 10% increase in R affect V? So we know that dV, well, now we want dV, delta V is equal to 4KR cubed delta R, because that is the change. So the relative change is we would divide it by the original equation, so KR to the 4th So this gives us k's cancel, those go away, cancels all of that. So 4 delta r over r. So the change in the volume is 4 times the change in the radius, is essentially what it is. So a 10% increase in the radius will produce a 40% increase in flow. Uses 4 times as much. Okay, sensitivity of change. You want to calculate the depth of the well from the equation S equals 16t squared by timing how long it takes a heavy stone to drop the splash in the water below. How sensitive will your calculations be to a 0.1 second error in measuring the time? So delta S is equal to 32t delta t. Okay, so the issue here is it depends on how much time has passed. Because the bigger t gets, the bigger this number gets. So like when t is 1, delta S is 32 times 0.1, or I'm off by 3.2 feet. At t equals 2 seconds, that's going to be 64 times 0.1. So that gives me 6.4 feet. So it actually depends on how much time has actually passed. Okay, and the last thing we got here, Newton's method. So Newton's method lets you approximate zeros by essentially bouncing back and forth. You choose some random value to start at, and then it should collapse you down towards a given value. So let's see here. You need to choose some random x value first, essentially. So f of x, and then you divide by, so we'll start at, let's say, negative 0.3. So normally you look at the graph to kind of approximate this. So minus f of xn would mean I'd plug negative 0.3 cubed plus 3 times negative 0.3 plus 1 all over the derivative with it plugged in. So 3 times negative 0.3 squared plus 3. If you work this out, this comes out to be negative 0.322232415.9. And what you do is you actually then take this number and plug it back into your formula, and you keep repeating the process until the numbers start repeating. And eventually that value will be your approximate solution. I'm not going to work through it because it's just repeated arithmetic. This gets plugged into that, you get an answer out. Then you plug it back into that, answer out, plug an answer in, out. And you just keep cycling until the values start repeating. The problem with this is if you choose poorly, you'll never collapse down to a single value. So, and also with modern technology, this process isn't really needed anymore. But that does bring us to the end of the section.